Alright, so we have here a static equilibrium problem. This horizontal platform that we're looking at has an unknown length and a mass of 13.5 kilograms. Right, so the mass of the platform, 13.5 kilograms. On the left end, it's attached to the wall, and on the right end, you have a box of unknown mass. So the mass of the box is not known. We're told that the tension force in this rope is 982 newtons. The rope is connected to the center of the platform, makes an angle of 28 degrees with the horizontal. Alright, so we want to find the mass of the box, and we want to find the horizontal and vertical components of the reaction forces. Alright, so let's see here. Let's start by looking at our forces on the rod. The forces acting on the rod, well, gravity, there's the platform here, so the mass of the platform times g, and then this box is pushing down on the rod. Now, keep in mind the platform is pushing back up on the box with the normal force, but in static equilibrium problems, we are limiting our analysis only to forces that are acting on the rod. The box pushes down on the rod, we're interested in that. The platform pushes back up on the box, we are not interested in that. Alright, I've got tension here. What else? There's no applied force. There's kind of a, well, if we look at the reaction forces, okay, so we've got a horizontal component of the reaction force and a vertical component. I'm assuming that the vertical component points up. I may be wrong. But those are the forces that are acting on this end of the rod over here where it's attached to the wall. And that's it. Those are all the forces in the problem. So, static equilibrium tells me that I sum all my x forces, so that's FH, my sign convention, I guess I need to put in here. That's positive, and of course counterclockwise is positive. So FH is positive, and then the only other force that has an x component is Ft cosine 28. Right, the x component of Ft goes sum to 0. For the y forces, I have four of the 5 forces have a y component associated with them. There's the vertical force, which is positive. There's the y component of tension, which is positive. And then minus gravity for the platform, minus gravity for the box. Okay, and then the sum of all torques, well, I'm going to choose this here as my pivot. Right, you always want to choose your pivot. Well, you don't have to, but you want to choose your pivot where you have the most unknowns. And FV and FH are 2 of my unknowns, so I'm going to put my pivot there, which means that the only torques in this problem are the torque due to tension, the torque due to the platform's weight, and the torque due to the box's weight. There is no torque due to the vertical reaction force, and there is no torque due to the horizontal reaction force, right? Because the distance from the pivot to the point of application of those forces is 0. All right, let's solve these torque equations real quick. Okay, so the torque due to tension. Well, tension is making this thing rotate in a counterclockwise direction, so it's positive. The distance from pivot to the point of application of force is L over 2, okay, where the rod has a length of L. The tension force is Ft, and then the angle here, here's my R vector, and so that angle there is 180 minus 28, which is 152. Okay, so next, tension due to the platform. Well, that's minus. The platform's trying to make the platform's gravity is trying to make the platform rotate clockwise. L over 2 mg sine 90. Right? And then the torque due to the box is also minus. It's L, and then the mass of the box times g times sine 90. Alright, so if I sum all of my torques, I get plus 1/2 L times the tension force times sine 152 and then minus 1/2 L times the mass of the platform times G, and then minus L times the mass of the box times G equals 0. Now the L goes away. Right, I can divide every term by L. I can even divide 0 by L, and it's still 0, so who cares? So this first term becomes 230.5. The second term becomes minus 66.2, and the third term becomes minus 9.8 MB. So I get 164.3 is equal to 9.8 times the mass of the box. So the mass of the box is 16.77 kilograms, which I guess I'll round off to 16.8 kilograms. Alright, what about the horizontal and vertical reaction forces? Well, the horizontal reaction force, that should be easy, right? If I look at the sum of all x forces, again, that's horizontal reaction force minus 982 cosine 28 equals 0. So that's easy enough. The horizontal reaction force is just 867 newtons. Let's see if we can figure out the vertical reaction force. That's Fv plus 982 sine 28 minus the platform weight minus the box's weight. So we did need the mass of the box to get this one. Alright, so this is this is 461 minus 132.3 minus 164.6. Those sum to 0, right? So if I solve for FV, I get FV as minus 164. So that minus sign just means that I got the direction wrong. That the vertical reaction force is actually 164 newtons and it's in the minus y direction. And that can happen if you guess wrong on the force. No big deal. We just have to indicate. Here, we have to, make a point of noting that our diagram was wrong so that our answer is clear.